Good afternoon, everyone. I hope you can see the screen. So, someone just reply on the chat if the PPT is visible to you and you can hear me also. Just any one of you. Okay, fine. So, we were into this, the algebraic system. I discussed with you group. Today, we intend to discuss ring and field. So this is broadly, we are just giving you the definition and examples just now of group ring field. Later on, I will go into more details of this. So very fast, in 5 minutes, this is what we have done. I will share this presentation with you. It will help you actually. We said that the algebraic system looks like this. This is how your algebraic system looks like. You have examples like n plus, z plus minus, or r plus, and maybe two operations more, multiplication and subtraction. So these are all your algebraic systems. Your natural number is 1, 2, 3, 4 till infinity. Z is including 0 and all the positive and negative integers. Q is the set of rational numbers. R is the set of all real numbers. So generally, we will have only these to deal with. Then we defined what is a binary operation, and we told you that for any two elements, you will have something like this, that A star B will belongs to A for all AB belongs to A. That's the simplest way of uh, telling you what is a closure property. The set of natural numbers is closed with respect to addition and multiplication and not with respect to subtraction and division. Okay. Now it is visible. Uh, it was not visible. I hope you can see this. I'm sharing this PPT.
It's visible.
It's visible, no? Okay,
Yes.
fine. Okay. Okay, so in very short, we just told you about the natural number and the number system, then the binary operation, and some examples of algebraic system which consist of a non-empty set A and one or more binary or closed operations. So this is just overlook, just to view it, what we have done already. Then these are the just in one slide, the properties which I have already discussed with you. So closure property was the first one. So that was your G1, you can say, the closure property. Then associative property, which is written here, that should be your G2. Identity should be G3. Inverse should be G4 because these four gives you a group as we told you in the last class. And finally, commutative property should be G5, which will give you an abelian group. So just few seconds, look at this slide and tell me if anyone has not followed anything, because when I discuss ring and field, I will be referring these properties again and again. It will be related to these properties only. So G1 is the closure property, which is already discussed in the last slide. So I'm not going into it, or the binary operation. G2 is the associative property, G3 identity, G4 inverse, and G5 commutative law. So from G1 to G4, it's for group, and G5 is for abelian group. If you have understood, fine. If there is anyone having any question in these five properties, very fast, just write to me in the chat. Okay, I have not said anything new, Rima, actually. I'm just repeating last class things. We are just telling you the five properties of a group. Okay, we have already discussed this. So we have just told you that from G1 to G4 we get a group, and then with G5 it is an abelian group. Okay, next. Very important that if only the closure property holds, then we have a groupoid, like we told you already. Then semi-group if closure property and associative property. Okay. So that's your semi-group. Yes, identity is there in monoid. So we are just telling you here. So if you have, okay, last slide. So for identity element, you should have an element E belongs to A such that your A star E, this is a relation, equals to E star A equals to A. That means I should get an identity element E such that when operated with all the elements, it gives back the same element. For example, addition and the set of integers. 0 is the additive identity, because to any number, if I add 0, I get back the number. This is how we define an identity element. Okay, so if I'm adding 0, so additive identity is generally 0 and multiplicative is 1. So suppose I am multiplying 1 with the number, I get back the same number. This is your A star E equals to E star A equals to A. That means I get back the number after doing the operation with the identity. This is your identity. This is what we mean by an identity. Okay. So in one slide, you can get the commutative law, A star B equals to B star A, associative law, then the identity, then you have the inverse. Okay, so as I was telling you, semi-group is your till associative property. So here are some examples of your semi-group. N plus, N dot, N minus is not a semi-group, we know already. Then we have what is a monoid. You should know this. So by monoid, we mean that if all the three conditions hold together, that means it has to be closed. It is an associative. The operation is associative, and also there is an identity. So till identity is your monoid. Finally, group, as we were discussing. All the four properties: closure, associative, identity, inverse. And if the commutative law holds, then abelian. Okay. So, Niladri, is it clear to you? Have you got what is an identity? Niladri Sen,
Yes, ma'am.
have you understood what we mean by an identity?
Yes, ma'am, it's clear.
Can you tell for the set of rational numbers and the operation is addition, what will be the identity element? Just try, okay? There is no harm.
Rational number only.
Yes.
Okay, ma'am.
Yes, I did not get your answer.
Ma'am, rational number only. The number will the answer will be that number only itself, because it's the identity.
Can you give an example of a rational number? Any rational number?
5.5.
Okay, 5.5. This is a rational number, okay? So,
Yes.
what should I add? Because operation is addition. So what should I add to 5.5 so that I again get back 5.5?
0.0.
Yes, so this is the identity.
Yes, ma'am.
Okay, so identity means whatever I am adding to the number and I am getting back the same number.
Yes,
So
ma'am.
if it is rational numbers and multiplication, what will be the identity?
1.
1. And I'm sure now you have understood actually.
Yes,
Okay,
ma'am. Yes, ma'am.
fine. Yeah. Symmetry, no, that's different. Symmetry is not here. Okay, that's different. We will do symmetry actually, but no, this is not about symmetry. Okay. Okay, so that was group and abelian group. Then we have this theorem which we will do step by step. As I told you, first I want to finish ring and field today, the definition and what it is about. Actually, this is a huge topic. There are endless questions, endless theorems, and lot of examples. Actually, lot of types of questions to do. But as per your syllabus, it is only a one module, one part. This is not an entire course for abstract algebra that we do everything and all of it. So I have just explained in the last 2-3 classes what is a group. I given you some idea. Today I will tell you about ring and field, and then some questions we will do. and maybe we will not go into that details as it is. Yes, Shivandu, that's different. I will tell you symmetry, but it's not just now in this topic. Okay, that's okay. So here we have some very few theorem to look at just now. I'm not going into the details now. That identity element is unique because our work is more application based. We are not so much interested into proving theorems of 2-3 pages and going into the theory of all these things. Okay, so you should know these things so that when I solve certain numerical problems, certain problems, because we have done examples in the last class also. So identity element is unique. So identity can be 1, can be 0, and all these things. Suppose identity contains A and A is having different values, then we solved the question last class, it is not unique. So only you need this idea to apply in the question just now. So identity element is unique. Your inverse has to be unique. Cancellation laws hold good. This is the third theorem we have actually, that if A star B is equals to A star C, you have B equals to C. This is the left cancellation law. There are a lot of questions with the cancellation law. We'll solve some examples after this. And A star C equals to B star C gives me A equals to B. This is the right cancellation law. The fourth theorem says that A star B inverse is B inverse star A inverse. So this, just keep it with you as the laws just now, inverse law and cancellation law and so on. We will solve questions after some time. In a group, the identity element is its own inverse. Yes, we can prove this also, that for a group, the identity element is its own inverse. The order of a group, the number of elements in a group is called the order of a group. So suppose we did in the last class 1 minus 1, I and minus I. 4 elements we considered, isn't it? So this is a group of order 4. So the number of elements give you the order. Okay, finite group. If the order of a group is finite, then G is called a finite group. So just very basic definitions and theorems actually. The proof we are not doing immediately. Okay, so what was intended today was again something very simple, very easy. That is, what is a ring, what is a field, and some examples of it. So I start with you. What do we mean by ring actually? So you can see here a very easy way they have defined actually. Consider a non-empty set R equipped with 2 binary operations. So first of all, till now in group you had only one binary operation. Now in ring you will have 2 binary operations. So you can see there is a O and there is a star. You can take also addition and multiplication as the 2 binary operations. Okay, so they have defined here the ring as considering a non-empty set R along with 2 binary operations, such that for the first binary operation, that is O or plus, you have to show that it is an abelian group. That means all the 5 properties. Okay, so 2 binary operations are given, so addition and multiplication. So under addition, you have to show that all of the 5 properties holds. Okay, till there. Then for multiplication, only till semi-group. That means closure and associative. Okay. So first, you have to prove for addition till abelian group, a semi-group for multiplication, and then you have what is known as the distributive law. So this is your distributive law, which looks like this. You can also write it like this: A dot B plus C is equals to A dot B plus A dot C. This is one distribution law, and the other one is here. So both are not same. Okay, so you have to say distributive law 1 and distributive law 2 if you want. B plus C dot A is equals to B dot A plus C dot A. So these are your 2 distributive laws. Okay, so for a ring, so you have to remember what? You have to show that under addition till abelian group, then you have to go for till semi group for multiplication, and then the 2 distributive laws. So if you can show all this, then the non-empty set R is called the ring for the two binary operations, addition and multiplication, or you can generally denote them by a dot and a star. Okay, so this is how we define a ring. So keep the definition with you. You have to solve problems, then only you know you have understood. Okay, so you can see here there is a note saying that O refers to addition and star refers to multiplication. Although these operations need to necessarily have the meaning they have in arithmetic, so they can be defined in different way also. So for multiplication, if you remember, only till associative property. Okay. After that, if the ring has a multiplicative identity 1, it is called a ring with unity, because my second operation is multiplication after addition. So for addition, I have shown all the 5 properties. That is, we have shown till abelian group for plus, and for multiplication only till associative. Then it is a ring along with the distributive laws, definitely. Now, if the next one comes in the picture, that is identity for multiplication, and the multiplicative identity is 1, as we know, it is called a ring with unity. Okay. Commutative ring, a ring R is called a commutative ring if the multiplication operation is commutative. So if you have the multiplication, nothing is being told about inverse here with respect to multiplication. Okay. So commutative ring is only a till ring, and then if you can show that the multiplication operation is commutative. Okay. So next we have an example for you. Let us take the whiteboard actually for 2z plus. Yes. Okay, so we have 2z plus dot. This is the algebraic system given to you. Okay, that means it contains all the even numbers 2, 4, 6 and so on. Addition, and you have multiplication as this. So you can check here. They are saying that consider the set of even integers denoted by 2z with the usual addition and multiplication as the two operations. This is a commutative ring without an identity. Okay, so this is an commutative ring without an identity. Actually, I told you the answer. We will now prove it. Okay, so this is what a commutative ring without identity. Okay, so let us start with it. Let us start proving how it is a commutative ring without identity. Okay, so what we do here at the beginning to start with, if you can check here, we have with you all these properties to show one by one. So the first property which you will be showing here to begin with, the first one here, that under the addition, it is an abelian group, and under multiplication, semi-group, then the distributive laws. So this is how it goes about. Okay, so first we start with that 2z plus is an abelian group under, this is the first proof I have to show, 2z is an abelian group under addition. This is an abelian group under addition. Okay, so this is my first proof I have to go about with. Then 2z multiplication is a semi-group under multiplication. This is what I have to show. And finally, the distributive laws I have to go about with. Now, if I can show till here, then we called it what? Simply a ring. So if all these are completed, then this is a ring. Okay. After this, commutative ring, the thing comes about commutative ring. So after it is a ring, to show that it is a commutative ring, I have to show under multiplication it is commutative, and then finally about the identity. Okay, So just try this question. Anyone who wants to elaborate on this question? Anyone who wants to solve it and share with us? Any question about this? Have you understood the question? The question is here once more for you. This is the question we are trying to do. Consider the set of even integers denoted by 2z with usual addition and multiplication is a commutative ring without an identity. Have you got the steps? What we have to do? Anyone has anything to ask that you have not understood? Okay, so let us have one volunteer. Someone tells me the first part, that 2z plus is an abelian group. Who will speak? We need a volunteer to speak on this.
Uh,
Your name, please.
Tomojit.
Yes, Tomojit. Okay.
So,
Start.
so for 2z plus to be a abelian group, we first have to prove that it's a commutative group.
Yes, that means all the 5 properties.
Yes, yes. All the
So
5
2z
properties must
2z
hold true.
plus will have what type of elements? Can you tell us?
Even number. 2z even integers.
Yes, so can you tell the even integers? It starts from where?
It start from actually integers. So minus. Actually, a elements will be 0, 2, 4, 6 like this. In the negative domain, it will be -2, -4, -6 like this.
Yes, very good. So this is how my set looks like. I couldn't write plus minus just now here, so I'm writing this as separately. So actually 0 will be there, and we
Yes.
will have plus minus 2, plus minus 4, and so on. So this is
Yes,
how my
yes.
set looks like. Yes, Nilanjan, till plus infinity and minus infinity.
Minus
Yes.
infinity.
Okay, so now first I have to show that this is an abelian group under addition.
Yes.
How will I proceed?
So first we have to prove the closure property.
Yes, under addition.
Yes, yes.
So
So,
first we will move with closure property under addition. Okay.
yes, addition.
So
So,
is it closed or not?
yes. So this group is actually closed.
Closure
Because
under addition.
yes. So even numbers adding even number will always return a even number
Yes.
only.
Right. So if I add any two even numbers, I will always get back another even number. So with
Yes.
this logic, I can say that fine, it is closed under addition. This is the first one. Okay.
Yes.
So let me just clear this once more because I wanted to keep it clean actually. So the first is, it is closed under addition. Okay, so we are considering 2z plus dot. This is the algebraic structure we are going about with. Okay, so it is closed under addition. Then second,
Second, we have to prove that it's associative.
yes. So if it is associative or not under addition. So what is your answer?
Yes, it's actually
Why?
associative because if we mean like that in the what we did previously means
If
two
we take any
even numbers, yes,
even numbers,
and
yes,
add them by changing their order, the outcome is
same.
always the same.
Very good. Yes. Third, what is the third one?
Third, identity. We have to
Yes.
find the identity element. So addition is there, zero
Yes.
is there, so zero is the identity element.
Yes, so here the additive identity is 0 because to any even number, that means I
If you add
showed you
zero,
the
it remains
numbers,
the same.
it remains the same 0 plus minus 2 plus minus 4. If I'm adding 0, I get back the same number. Okay. Fourth, what is the fourth property?
Fourth, I forgot.
Inverse.
Yes,
Someone
yes,
wants to
inverse,
help.
inverse.
You need help from someone, ask your friend. If you have spoken a lot, you think you can ask someone else to continue. Anyone to help Tamojit after this, because we have a long list to go. Who wants to continue after him? No one. None of you understood what we are doing. 48 of you are here. No volunteer. That's surprising. There is none of you to speak actually. We are doing something so simple. We are just
So,
considering the even
Ma'am,
numbers. Yes, yes.
so
Say.
yes, it's actually an inverse property because like
Take an
the
example.
identity. So if the inverse
Two.
of a number like 2 and 2 plus of minus 2 returns
Yes.
the
Identity.
identity element.
Yes, so that means I can even say like this: a plus a dash, the identity should be 0. I mean, sorry, yes, the identity is 0. So my a dash is equals to minus a.
Minus a.
So negative of any even number. So if I take any even number and the negative also is another even number. So in this
Yes.
case, yes, fine, the inverse will exist under addition. So a
Yes.
dash is minus a means if I take any even number and the negative is again another even number only.
Yes.
Fifth, commutative.
Fifth is commutative. So a plus b and b plus a is
Yes.
always the
So,
same.
yes, so if I'm adding two even numbers, say 2 and 4, and if I'm adding, changing the order,
4
4 and
plus
2,
2.
nothing changes. So all
Yes.
the 5 properties, so in this way, you have to show and tell actually about all the 5 properties first with the even numbers under addition, that it forms an abelian group. Okay, so this is the first part actually. If you can check here, we have told you in the definition. In this case, this is, so till now we have only done this portion, this one, that R plus is a commutative abelian group or commutative abelian group, whatever it is. Okay, so next you have, what will be the sixth one to go about with?
Semi.
That means what? You have to show semi group for multiplication. That means you
Yes.
have to
Yes.
show what? Before associative property, you have to show closure property.
Yes.
So closure with multiplication you have to show. And my 7th point will be associative with multiplication. So
Yes.
just tell me, what do you think about closure and associative property for
So
even numbers?
multiplication. For multiplication, closure is whole true.
Why?
Because like even multiplication of even any two even numbers will always give a even number.
Yes, very good. Because if I multiply to even numbers, I will be always getting another even number. There is no doubt
Yes.
in this. Okay, so
Yes.
that's very simple. That closure property will hold.
Yes.
Now
And
multiplication and associative property and even numbers.
yes,
What do you
associative.
think?
Let me think.
Yes, take your time.
Yes. So
Take examples. Take
yes,
3
yes,
even
I'm
numbers.
doing
2, 4,
that only.
6. 2,
2
4,
for
6.
6. So 2 into 4 into. Yes, actually for associative, it's
Yes.
also holding true.
Because if I'm multiplying the numbers by shifting
Yes,
the bracket, answer never changes.
never changes. Yes.
Actually, associative holds very good for addition and multiplication. The
Multiplication,
problem is only when you have subtraction and division.
division.
In short, okay. So associative property also holds.
Yes.
Okay. So that means till now we have shown abelian group under addition and semi group for multiplication. Okay.
Yes.
Okay, Tomojit, we will
Yes.
stop with you here. Thank you very much for responding. But at this stage, I want some answers from the others also. That if you
Okay.
have followed or you have not followed. Anyway, very good, Tomojit. Thanks a lot. But you can just mute yourself now because I need
Okay.
response from the others also. Thank you very much. Okay, so these 7 properties. Anyone who has not followed, not understood the question, you don't know what is going on here actually, what we are doing, God knows. So if someone is having anything like this, please come up, please tell us. And if you have followed, then it's fine. Next comes, I actually see monoid means identity, okay? But as per the definition, it's not required here. Just now I want to show that it is a ring. So for ring, you have till the first operation abelian group and you have semi group for the second operation, then you have the distributive laws. So next we will not proceed with monoid actually, but we will proceed with distributive law. That's the definition of a ring. So for a ring, you have to show abelian group. For the first operation, you have 2 operations for a ring. So for the first operation, you have till addition. You have semi group for multiplication, means only 2 properties. Then you have the distributive law. So just now monoid is not there. So I have done the first and second part. It's not over because distributive law we have not shown now. We have shown these 7 properties still here, and my set is 0, plus minus 2, plus minus 4, and so on. So simply even numbers you are adding and you are multiplying even numbers. This is what you are doing. Okay, anyone who has not understood anything of these 7 points which I was discussing? The question was like this, which we were doing. Again, I will repeat for you. Consider the set of even numbers, even integers actually 2z, usual addition and multiplication. You have to show that this is a commutative ring without an identity. That means first you have to show that it is a ring. Okay, associative part, yes, I am telling you. So first we have to show that okay, first you have to show that it's a ring, then a commutative ring, and then without identity. Okay, so what you have to show, 2z plus dot is a commutative ring without identity. So first you have to show that it is a ring, then you have to show it is a commutative ring, then you have to show it is a commutative ring without identity. This is how it goes about. Okay. So associative part, I think you are asking me about the multiplication part. So as per the associative law, I will be taking any 3 even numbers, say 2, 4, 6. So if I am multiplying 2 into 4 into 6, this will be same as 2 multiplied by 4 and then multiplied by 6. This is your associative law. A composed B composed C is equals to A composed B composed C. Okay, so this is your multiplication and associative law. You are asking for the 4th and the 6th point. Okay, so the 4th point is inverse and addition. Okay, so here the numbers are what? First you have to visualize the thing. This is something very simple we are doing actually. So here the numbers are 2, 4, 6 and also minus 2, minus 4, minus 6 and 0 is there. These are your numbers. So inverse, when we are trying to do actually, you take any number, say 2, and you ask the question, what should I ask so that I get back the identity 0, because the additive identity is 0. Okay, so just wait a little bit because we have 5 minutes. I need to take the attendance and maybe once more, fresh as you join in after I take the attendance, I will just go over through this entire thing once more. Because your attendance will go if I don't stop here now. Okay, so I think most of you have joined. Many of you have vanished too. Anyway, that's up to you. So this is what your question is, that you have to show that 2z plus dot is a commutative ring without identity. So it is very important for you to understand how does 2z looks like. So your 2z contains 0 and elements like 2, 4, 6, someone had mentioned till infinity, and also the negative elements -2, -4, -6, and so on till your minus infinity. Okay, so whenever you are trying to do any property or anything, don't do anything arbitrarily. Okay, so just be very precise actually what you are trying to do. So here we are just trying to tell you that it is the numbers looks like this: 2, 4, 6, -2, -4, -6, and so on. So you will be dealing with these numbers for all the properties. Now if I have to show commutative ring without identity, first I have to show, so my first step, I have to show that it is a ring. This is the first thing. Second, I have to show that it's a commutative ring. Okay. Third, then I will show there is no identity. So these are the 3 steps to the question. So for the question, the first step is you have to show that it is a ring. Then second step, it's a commutative ring. Third step, there is no identity. Okay. Now, since I have 2 operations here, actually, I'm dealing with addition and multiplication. You can check here, there are 2 operations actually to go about. So this is the algebraic structure. So you are having addition and multiplication, which I'm putting it as a dot here. So these are the two operations you are dealing with, addition and multiplication. So when we are talking about ring, that means you have to show all the 5 properties actually. Okay. Till abelian for your addition. So 5 properties. That means closure, associative, 5 properties for addition, identity, inverse, and your commutative property. Okay. So this is all you have to show actually. First the 5 properties. Then you have to show 2 properties for multiplication. That is, you have to show till it is a semi-group. So this is your definition. Okay. So these are the 5 properties I'm mentioning, and these are the 2 properties, closure and semi-group. Okay. And then you have to go for the distributive laws. So here the third point is after this, that distributive laws. So when I have shown all this, then it is a ring actually. Then when I say commutative ring, that means I have to show that A multiplied by B is B multiplied by A for the set of even integers. This is commutative ring. No identity means for multiplication, I have to show that there is no identity. Okay, so this is the entire structure actually of the question and the solution. Anyone has any question here? Have you understood actually what we have to do? So I have not solved, I have just given you the structure of the solution. What are the 3 steps, and inside the 3 steps, what you have to do? Anyone having any query? Anything you have not got till here? Then we can go step by step. So for the first step, it is only that you have to show a ring. That means abelian group till addition, semi-group for multiplication, and distributive laws. Then commutative ring means after multiplication, we will come to it how to prove it has no identity. It goes about with the same thing actually. Identity means what? For multiplication, you have no. So you have to go about with like this. Like we have the property for identity. How you show? A star E equals to E star A is equals to A. This is your formula for identity. Okay. So in this case, now you just take any even integer, say 2, and you ask the question, what should I multiply here to get back to? The way we do for, we find out identity. Okay. So what is your answer here? For the set of even integers, what should I multiply to 2 to get back to? Yes, Oishika? Right? 1. So that means the multiplicative identity should be 1. Now 1 does not belong to the set of 2z. So there is no identity. This is how it goes about. Okay. So actually 1 is the multiplicative identity. So if I am multiplying 1 actually to any of the even integers, I should get back the even integer. There is no other multiplicative identity. But 1 does not belong to the set of even integers. You know, 2z looks like 2, 4, 6, minus 2, minus 4, minus 6, and so on. Hence, we say that there is no identity. Have you got it? Whoever was asking, I mean everyone, it's for everyone actually. So this is the third step actually where we show that there is no multiplicative identity. So it is a commutative ring without identity. Whenever I say commutative ring means till addition I have shown everything. So for multiplication there is no identity. Because 0 belongs to 2z, so there was no problem with the additive identity. Only here we have problem with the multiplicative identity. So Oishika have understood, one person has understood till here. Anyone else who have understood or not understood? Okay, Adrita, you have got it. That's good. It shows you have got it because you have written it confidently. But what about the others? Can we have some response from you? Okay, Pratyusha, you have got it. Orko, you have got it. That's good actually. Sweta, you understood. That's good. Okay, so we have 4-5 responses who have understood. Is there anyone who have not got it? So again, I repeat that I don't know if the solution is there. I don't think the solution is here. So please try to solve this on your own also. You just try to show it's a ring, then try to show it's a commutative ring, and then you try to show there is no identity, because identity 1 does not belongs to the set of integers. Okay, maybe you are bored now with this same question. It's been long we are doing this. So let us move on to some other question, and let's see if you have understood ring. So, okay, distributive law I did not do with you, but it's okay. You have understood till now, I think, that what we mean here when we are trying to talk about the distributive law, it is nothing but your A dot. This color is very light. So, distributive law is your A dot B plus C is equals to A dot B plus A dot C. So it can be verified. This is the left distributive law, and the other one is your right distributive law. So, okay, Niladri, you got it. That's good actually. Finally, Anjali, also you understood. Okay, is there anyone in the chat who have any problem, anything you have not understood? Okay, Kamajit, you got it. That's good. Okay, fine. We have quite a lot who have understood this. Maybe first time you need another time to go through it, another 2-3 times before you get the entire thing. That's fine. But this is a very good example about ring, actually 2z plus dot. Okay. So if you do this, it will be easier to solve certain small questions which I've skipped just now. So try to understand this. This will be very helpful. Okay, the distributive law, this I did not discuss with you. How will you show the distributive law actually? So as we were telling you, it was 2z plus dot. That means 0 plus minus 2 plus minus 4 plus minus 6 and so on. These were your even numbers, both positive, negative and 0. So if I have to show the distributive law, it's very simple as that. I can take any 3 numbers actually, say 2, 4, 6. Say 2, 4, 6, and very easily I can say that I can show that actually my RHS and LHS. So my right hand side is equals to 4 plus 6, 2 into 4 plus 6. That means 2 dot 10, which is giving me 20. Okay, and my left hand side is equals to A dot B means 4 into 2, 8 plus 6 into 2, 12, which will give me 20. But this has to be for all the elements. That is very important. Okay, so what you will say that in this case, that because addition and multiplication actually holds, so we can say that this operation will give you. So you have to give a proper explanation to the distributive laws. Okay, so you have to treat both the laws separately, not all together. So you have to say in this case that how you got left hand side and right hand side more general. So you have to give an explanation in terms of addition and multiplication, which is actually distributive over the set of even integers. So in that way, you have to bring an explanation. I will see if I get a write up. I will give it to you so that you can see how some solved answers will be there for you. But this is your distributive law where just now you will get it equal. So the writing part, let me see if I have a solved question, I will share with you. Okay, so this was quite a long one which we were discussing actually about 2z plus dot, but I think you got a fair idea just now what we are trying to say. Many of you may have not understood things very well till now. It's simple. You need a little more time. You need to look at these slides 2, 3, 4 more times. Look at this little more actually again and again. Ring theory, which I have just discussed with you. Look at the 3 points given here. So abelian group for addition, semi group for multiplication, and then the distributive law. After this, if you have the unity, the identity as 1, generally the multiplicative identity is 1. If a ring has a multiplicative identity 1, then it is called a ring with unity. So obviously my second operation is multiplication. So identity will be 1. This is why for the set of even integers, there was no identity actually. Then definition of commutative ring, if the multiplication operation is commutative for the given set, then you have a commutative ring. Okay. So this is what we have done here for today just now. So what was a ring? Then how we define a ring with unity. And if the unity is not there, like in set of even integers, there is no unity, then we will say that it's without identity. And then commutative ring if the multiplication is commutative. Okay, so the definition is once more, actually the entire topic is ring, fields and integral domains. We will do one by one. No need to hurry. I'm not going into anything else other than rings here because I got very few response just now. If you have understood things well, so slowly, nothing to hurry actually. With examples, we have to move out. Maybe next class we need to solve more questions actually with more examples for you. So you can check here the definition of a ring. Actually, if you understand the definition, things are simpler. So that's algebraic structure R plus dot. Here R is a non-empty set. You can think of it as a real number also. Is a ring under addition and multiplication. These are the two binary operations. Need not always be addition and multiplication. So such that R plus is an abelian group. So this is the first point. You have to show all the 5 properties that R plus is an abelian group. So associative, additive identity is 0, inverse, commutative. Okay. So because plus and dot are binary operations already in the definition, they have not started with closure property. So the definition says that we have 2 binary operations. Okay. So this is why we are starting with A1, A2, A3, A4. That's associative and identity and inverse and commutative. Then for multiplication, again, it is given that it's a binary operation in the first line. So associative is this, that is semi-group part, and distributive law, they have written with D. So this is another representation of the same thing which we are saying. That means I have shown abelian group for addition, I have shown semi-group for multiplication, and then I have shown the distributive law. Okay, all 3. So in this way, I have shown the definition of a ring. Special types of rings. So we have a commutative ring. If multiplication is commutative, we have a ring with unity. If the identity element 1 exists, we have already told you this. You know these things now. Okay. So here we have examples of ring. All of Z, Q, R and C are commutative rings with identity, because 1 as the identity element belongs to Z, Q, R, all of this. N is not a ring. So Z, Q, R, C are all rings. So I can ask you, show that R plus dot is a ring. The questions can be like this. Show that. So suppose I give you this question. Show that, let us take complex numbers. Show that C plus dot. Dot means multiplication. Okay. Or I can write it also like this. Show that this okay, just wait a minute. Okay, we cannot put it here. Fine. Okay, just wait. Let me write it in this way. Okay, so let us write it in this way only. Show that C plus multiplication is a ring. And then if you tell me if it is a commutative ring or if there is identity also. Okay, suppose the question is like this. So already Tamajit has spoken. We don't want him to speak further. So someone else, please unmute yourself and just tell me the points. How will you go about with C plus dot is a ring? Just the steps we are asking you. You don't have to solve anything. What are the different steps? How will you show that the set of complex numbers is a ring with respect to addition and multiplication? Okay, who will speak? Someone has to unmute yourself and speak. Who is the volunteer? We just want a volunteer who will speak on this. It is already solved, okay? It is said that it is a ring. You have to just tell me how to represent in your copy. Suppose I have given you this question, show that C plus multiplication is a ring. You have to just tell me the steps. What will you show? What will you write? Just tell me in words. You don't have to do it. Yes, who is coming up? I'm waiting for someone. Yes, Sweta, just unmute yourself. It helps others actually. Okay, so Sweta, you are speaking. Just unmute yourself. Like to hear your voice. Ah, your mic is not working. That's very unfortunate. Okay, anyone else other than Sweta? Actually, you have set the points, but you have to say a little more actually on this. This is why I asked you to just unmute yourself. So Sweta has answered. First, we'll prove that it's abelian. Now, what is abelian? What will you prove? When you say something is abelian, you have to tell me the set and also the operation. Both things. Second, semigroup. Which semigroup? Who is semigroup? Okay, still Sweta has said something. What about others? Is that much difficult? Or are you afraid to see the set of complex numbers? This is why I gave you. There is nothing special about the complex numbers. Your complex numbers contains the real numbers. It contains the natural numbers still there. So everything is under the complex number. Any number can be written as x plus iy form. Suppose I have the integer say 5. I can write 5 as 5 plus iota of 0. That's all. Yes, addition for abelian. So complex numbers and addition. That you have to show abelian. Yes, correct. Multiplication is for semigroup. That you have to mention. Okay, so complex numbers, and because here I have two operations. In group, it was very simple. If I said inverse, if I said identity, it was understood because there was one operation. But now, yes, Orko, we need to first prove that yes, C plus is abelian group. That means first I will be proving all the 5 properties of addition and abelian group. So can you tell Orko this will include what in short? We need to first prove that C plus is an abelian group. Right. This is what you have to show first. So if I have to show first that C plus is an abelian group, that means what I have to show? How many things? Yes, all the 5. Right. Under addition. Yes, very good. So all the 5 properties under addition. So this is my first work. Yes. So closure, associative, identity, inverse, till commutative. Because your definition says it's abelian group, not only group. Okay. So my first point here is to show that the steps you should know. That is important. Okay. So first I will be showing that C plus is an abelian group. So this is first I have to show that C plus is an abelian group. So when I say that C plus is an abelian group, that means for the set of complex numbers, all the 5 properties I have to go about with under addition, starting with closure, then associative, then inverse, then identity, then inverse. First identity, then inverse. Very important. And finally, commutative property. This is my first step. Okay, this is point 1 actually for solution of this question. Okay, what is the next step that I will go about with? What I have to show after this? Yes, someone writes. Okay, if you don't want to speak, you can write to me also. Yes, Orko. C star is shown that is a semi group. Yes. So you have to show for multiplication, closure, and associative property. Okay. So that means I have to show now. After that, C cross is closed and associative. Okay. So this is my second step. Yes, Shibendu, you have a question? Same. Commutative in here is same. Abelian group and commutative group is same. Okay. Abelian and commutative has no difference. The property we generally say as commutative, and the group we can call abelian or commutative. Both the same. The property is named as commutative. Okay. I hope you got that both are same. Okay, so my second step was that the set of complex numbers and under multiplication is closed and associative. What is my third step? What is my third step? Yes, semi-group is done. Yes, Sweta, distributive law. Yes, Orko. So now I have to show the distributive law. So my third step here after this is distributive law. Okay, so when I have shown all these three things, now I can say that yes, it is a ring. Okay, so if all this holds, I will say it is a ring. After this comes identity and multiplication. Okay, so after I have now said that okay, it is a ring. Okay, so now I have said that ring, proved that it is a ring. Okay, so now I have proved it is a ring. So after I have done all these things, now I have said that it is a ring. Okay. Now next, after I have said that it is a ring, now I will check on two things. Does it has identity under multiplication? So next I will check for ring with unity. So what will be your answer? What will be your answer for ring with unity? So I have proved it is a ring through all these three steps. Now I want to show if it is a ring with identity or not. So when I showed the three things, it is done that it is a ring. I have shown abelian group under addition, semi group under multiplication, and distributive law. So I have shown that it is a ring. Now I want to show if it is a ring with unity. Okay, so who is answering this? Is it a ring with unity? What should I check for a ring with unity? Or is it a ring with identity? Whatever it is. Ring with unity or identity. Same thing. No response? What happened? Is that so difficult? What I'm asking? Yes.
We will try to find a number that on addition or multiplying will return the same number.
Only
So,
multiplication, not addition.
Yes, only.
Yes.
Only multiplication. So,
Yes.
after multiplying, will return the same number,
Yes.
and
what is
if
the
it
answer?
falls in the same case or not, means
Yes.
in the same group or
Yes.
not.
Yes. It is if it is in the same domain or not. Very important.
Yes, domain or not.
Yes. So what is the answer?
Multiplication. So one will be the element, identity
Yes.
element.
Yes. And is one a complex number? Next question you ask yourself.
No.
No?
No.
1 is not a complex number.
Actually, if we consider 1 plus 0i, then it's a complex number.
It is a complex number. You have to keep this in mind, actually.
Yes.
This is how it looks, actually.
1 plus 0i.
Yes. This is the number system you forgot, actually. This is the set of complex number. Just
Yes.
remind it, okay? Under it, you have the set, which is the set of real numbers. This
Yes.
contains Q, set of rational numbers. This contains Z, which is the set of
Integers.
integers. I'm not going into any further because after integers you have natural numbers and all
Natural
those
numbers.
things. So your complex numbers contains everything.
Everything.
Okay.
Yes.
So definitely 1 belongs to complex numbers. You cannot
Yes,
say anything
yes.
else. Okay. Any number which is a whole number integer can be written as 1 plus iota 0.
Yes.
So this is definitely a complex number. Okay. Just to remind you, because we are doing so many things, you may have forgotten this. Something
Yes.
simple. So actually, whenever you are searching for ring with unity, you have to just check on the multiplicative unity. That's all. And multiplicative unity is generally 1. So if 1 is there or not, exception was 2z, because 2z has even integers. Okay.
Yes.
Yes, Shirish, right? It is unity actually because 1 is there. Okay. So 2z was an only exception which has no unity. But generally, the multiplicative identity is 1. And that 1 belongs actually to most of the sets. Okay. So we have yes as the answer, that it is a ring with unity.
Yes.
Okay, next comes if it is a commutative ring. So what will be your answer for that? Next question, is it a commutative ring? Is it a commutative ring?
We will check the commutative property for multiplication.
Yes, again multiplication, because your addition, all 5 properties are over.
Yes, yes.
Is it a commutative ring? What is your answer? Yes, Orko, correct. Complete
Yes,
answer.
yes. It's a
Yes.
commutative ring.
Definitely, multiplication will give you a commutative ring. Okay, for
Yes.
complex numbers also. Yes, Shirish has also answered correctly, right? Sweta has also answered correctly. So your answer is yes. Because if I multiply any two complex numbers, first I multiply one number and the second number. Now if I interchange the order, the answer remains the same. There is no difference. 5 into 3 and 3 into 5 makes no difference. Okay. So finally, the set of complex numbers under addition and multiplication is a ring. First thing we proved, it's a ring with identity 1, or it's a ring with unity, we call it. And also it's a commutative ring. Anyone has any question here which you have not followed? You can ask me. And it's very good actually, 2-3 of you responded, answered. It's always helpful in a discussion. I'm sure if others have not understood, you will make that effort to try to find out actually what you have not understood. You can ask me. If there is anything, any question, anything you want, you can ask me. So you can see here the examples of ring, that is very important. All of ZQRC are commutative rings with identity. Here the identity means 1, which is the multiplicative identity actually. The set of natural numbers n is not a ring for the usual addition and multiplication, because additive identity is 0 and 0 does not belong to the set of natural numbers. And similarly for multiplication, 1, these are binary operations, we do not have 0 element, and existence of additive inverse fails, such that this. Okay, so actually you don't have additive identity, multiplicative is there, but if you don't have additive identity, the first point is not happening, second, third point is not required for natural numbers. If the question is show that is a ring, then okay. So Sweta has asked a question that is very good actually. So she's asking us, just now I have discussed here with you that C plus dot or multiplication. This is what we discussed is a ring. Now she's asking what about C, then we have a multiplication as the first one and then addition. What about this? Is this a ring? Okay, any answer from you? So she's telling us that C plus dot is a ring, fine. What about C dot plus? What about C dot plus? So that means what is my first step to this? So first I have to check if C and multiplication, if this one is an abelian group or not. So this is my first check. So what is the answer? Then I have to check, yes, if C plus is a semi-group. Okay, let's put it together as she has asked all together. Okay. Then I have to show that if C plus is a
Ma'am.
semi-group.
ম্যাম
একটা একটা করে লিখতে দে আগে।
আচ্ছা আচ্ছা
Okay. Okay. So the other way around, actually, we have to show two things. I mean, if it is happening or not. See, under multiplication is an abelian group or not. First, you answer me this. Then you tell me if C plus is a semi-group. Yes. Whoever was speaking, Paul.
I think at distributive law will not satisfy.
Okay. What about C and multiplication? Complex numbers and multiplication?
Multiplication, closure property is holding actually.
No
Closure is
problem. Because if I multiply
Closure.
two numbers, I will get another number which is a complex number. Yes.
Yes.
Associative
Closure is
number
holding,
also no problem.
Yes. Inverse
Identity?
also holding. Identity inverse both are holding actually.
Identity inverse both will hold in the complex numbers except 0. Division by 0 will not happen.
Oh, division. Yes.
Because
Division by
multiplicative identity is 1. There is no problem in that. Okay. But when I'm finding inverse, my formula will be like this. No. A multiplied by A dash is equals to 1 because the multiplicative identity is 1. So my A dash is equals to 1 by A. So
now
it is
if
very
zero.
A cannot be 0.
Yes.
So there is a problem with the inverse here. So for the set of complex numbers, if the set is C minus 0, then only inverse is possible. Otherwise not. So you will get stuck here at the first step only that it is not a ring.
Yes.
Okay. So because abelian group is not formed for multiplication under complex numbers. If I consider first multiplication and then addition, my answer that this is not a ring. No. Because I will not get inverse. Then comes the other properties, okay? Distributive or whatever it is. Oh,
Okay.
I just cleared it. I just wanted to put one step away. Anyway, have you got it?
Yes.
Redo to nahi ekhane. Okay. Have you got it, Sweta? You are asking this. It is not a ring because simple answer is there is no inverse first of all. So the first step is not being possible. Okay, so just try it also on your own. That was a very good question actually. Just try to see how it is happening. Okay. Okay, so natural numbers also we said it's not a ring. Then consider the set of integers 2z. I think that I have discussed already a lot with you. So I will not go into this anymore. Okay, what does my next slide say? Okay, I will just show you this example. It is already solved in your notes. It is given to you, the notes I have given you. Just look at the question and the solution. I will show you more solutions actually. That will help you to learn how to write the answers. Okay, next class I will give you more solved questions actually. Okay, so this is the last question. Just 5 more minutes we will take. You can look at here. The question says, if two operations O and star on the set Z of all integers are defined as follows. So I have taken here two operations, O and star. I am not saying if it is addition or multiplication or whatever it is. And I have considered capital Z as the set of all integers. And I have defined actually a composition B as A plus B plus 1 and a star B as A plus B minus AB. So I have considered two operations. This is not addition and multiplication. Okay. Till now I was doing the most easiest thing. This is why I introduced ring initially in initial classes so that you were used to the things. Okay. In the next few classes. So addition, multiplication will be not there always. Now comes the real questions like this where the relations are defined. So you have lot more calculations and lot more to do here. So next class when you come, you should know what is a ring, what are the steps for rings. I mean, you should know that what you have to show, what is 1, 2, 3, 4, 5, 6 and what will you proceed with. So you can check here that you have to prove that ZO star is a commutative ring with unit element. So commutative ring with unit element means everything I have to show. I have to show that abelian group under O, first step. See, this is the first step. Abelian group under O. Then I have to show that star is the semi-group, then distributive law, then it is a ring with unity, and then commutative ring with unity. So everything will fall here. Okay. So you can check here, Z0 is an abelian group they have shown. The relation is A naught B equals to A plus B minus 1. Set of integers I am considering. So if I am adding two integers and subtracting a 1, it will be another integer always. Take any two integers, just add them and subtract 1 from it. Yes, I will get back another integer, no problem. The closure property holds. Associative property, left hand side and right hand side they have done and they have shown that both are equal. See, they have solved one side and they have solved the other side and they have shown that both sides are equal. And they say that therefore associative law holds. So you have to do the entire thing. There is no shortcut. Identity, they have gone with this and E is 1. This is what they got. A composed A equals to E composed A equals to A. So A plus E minus 1 A gives me E is 1. Inverse, very good. Again, they have gone with this. A composed A inverse is E. So A plus A inverse minus 1 is 1. That means A inverse is minus 2 minus A. I think we solved this also before last class. So inverse exists and commutative law also they have shown holds. So finally, after doing all these 5 steps, Z0 is an abelian group. This is what is proved here. Okay, so this is the first part. It's not over. Oh, the meeting will end in 5 minutes. Okay, so very fast we will have to move now. Next slide here. Then as I told you, Z star is a semi-group. This is what they have shown. So star is closed, star is associative, star is defined in a different way. It's not same as O. Then finally the distributive law. So after this is the third point, the distributive law. Okay. So all these calculations for distributive law, both the distributive laws. Hence, this is a ring. This is what they have said. Then they have tried to show that commutative property holds. Hence is a commutative ring. Oh, unity they have not considered here anymore. Okay. So whatever it is, these were the steps. This question is done to you. Whatever I did, I will share with you in the Google Classroom again in PPT. So just go through these things. I hope in the next class, you will be in a better position than today. There will be more than 5-6 people to interact. You have to unmute yourself. You have to speak. You cannot only be silent like this. Okay. So let me take your attendance before everything goes away. 2-3 minutes are there. Is there anyone having any particular question to ask before I end the meeting? Is there anyone who wants to say you have not understood anything what was done today? because most of you have not responded. There was only, I can count few who only answered. Anyone there wants to say anything? Any major comment you want to make? You are most welcome. Okay, so maybe just now you don't want to speak. So the notes will be given to you. This example is already solved, also given. So please go through all these things, and maybe you can let me know in the next class if there's anything you have not followed or understood. Okay, so that's all for today.